So today we're going to focus on HART. All right, now looking at the screen now, it says analog. Well, before we get into the world of HART, we need to understand the world of analog because HART is based off of analog. So when we get into the world of PLCs, you have basically two main input options: discrete or digital inputs. All right, those would be either a 1, right, or a 0. So you have a 1 or a 0. That's basically it. That's all you get. And for the most part, discrete handles kind of like everything you really truly need. All right, limit switches, push buttons, proximity sensors, temperature sensors can be this way. Like, this is really all you truly need for a simple system. Now, when you start getting super duper complex, analog becomes a necessity. But for the most part, you can kind of get away with discrete, just zeros and ones, especially for sensor inputs. Outputs, that's a different game, especially now with networking, especially. Because, again, like turning a motor on, you used to turn a contactor on. Boom, just hard contactor engage. That would just full power to a motor, make it spin up. Not the healthiest thing in the world. We invented things that are self-starters, so when you would do that, it would actually like slowly try to like put like half power in the motor instead of full power, so it would start spinning slower, and then you would go to full power, so it was like a 2-stage or maybe a 3-stage system. So, you know, but that's still just a discrete, turn the out motor on type of thing, and it works just fine. So discrete really gets a lot of things done, right? Turns lights on, can turn conveyors on, heaters, those types of things. All right. But if you start needing true, like, nice control of things, then analog is where we start heading into. Stepping back to the world of discrete for one moment, the other option nowadays with discrete is a VFD. All right, VFD, variable frequency drive, which is how we actually change the speed of induction motors, is we change the frequency of the power going to them. So traditionally here in the US, we have 60 hertz frequency for our AC, and the speed is always based off that 60. But if you need to be able to slow a motor down or speed a motor up, VFDs are what we use, and they are literally changing the frequency that is coming out. So normally you'd have your frequency, you know, something like this. That'd be your 60 hertz, and if you had a faster one, say 30, it would be like this. All right, and we're actually just adjusting the frequency of that sine wave. That's how we actually control things. But like even VFDs, you could have an input, and you just say, turn the motor on, and that would then speed it. It would slowly ramp that thing up to speed now. So we don't have to do a hard chunk anymore to turn motors on. Yes, VFDs are more expensive. You're looking at like $500 or $600 depending on the VFD you're buying. You can go cheaper, like if you're just going from China for something for your home shop. But if you're going to go for a nice industrial grade something, it don't cost you. All right, and that's like $500 for a 2 horsepower one from Allen Bradley, and I don't know what type of educational discount we're getting, but I legitimately was looking those up recently. So I'm like, I need some VFDs in here. 15,000. 100 horse for 15 grand. That's just a little bit, but they're out there. Most of the time we network our VFDs, so you're not actually turning an input or output on. You're actually sending a network command, but you can actually wire up a VFD with inputs and say, and even true speed, you could say if this output is true, or input on the VFD is true, go to low speed, and this output's high speed, and if both are true, we go to a medium speed. So we actually do have that like crazy capability, which to me is kind of interesting. So just kind of something to think about in the long run. But yeah, so discrete, they're either 0 or 1, on or off, true or false, whichever verbiage you like. They all mean the exact same thing. However, when we get into the world of analog, you have two options. You either have voltage or current. So are you measuring the voltage coming in, or are you going to measure the current flowing? That is your two options. Oftentimes, the analog input or output cards have both capabilities. So you can be like, oh, we're going to send a current signal, or we're going to send a voltage signal, or we're accepting that. So it's a matter of like checking a checkbox. But you do need to be careful that check the modules that you're ordering either have both capability or have the one capability that you actually care about. So just something to be aware of. When we are dealing with voltage, we are traditionally in the either 0 to 10 volt area or the negative 10 to positive 10 volts. That is our signal range. All right, which gets the job done. It does what it needs to do is really what it comes down to. However, we don't really like voltage because of electrical noise. Having an analog wire by an AC line will induce things and cause spikes and things like that. So we really don't like voltage measurements, and so you can avoid them. Not saying you can always avoid them, but when you can, it's really best to go with the current measurement. Now, this is where, to me, it's really quite interesting. In the world of current, all right, so voltage was, I said, either negative 10 to 10 or 0 to 10. All right. In the current world, we're either 0 to 20, this is milliamps, this is volts, or 4 to 20 milliamps. Now, why would we use 4 to 20? Like, why are we just giving up 4 milliamps of range? Anyone have an idea? That might be part of the reason. But the reason that I know is for sensor detection. If your sensor is always outputting 4 milliamps, you know it's there, right? Where if the wire would get cut, it would now say 0, and your PLC could throw a warning flag saying this sensor doesn't exist anymore. Where if you use 0 to 20, or even that 0 to 10 volt range, and it's 0 volts, like the bottom of the sensor range, your PLC goes, is it there, or is it just reading that there's no liquid in the tank, type of thing. So that is a game that you have to play. So that is why, personally, I'd go with the 420 milliamp option, because it allows you to detect that, yes, my sensor is actually existing. All right. Now, things that we might have to do. So examples for analog. You could do temperature sensors, light sensors, level, distance, pressure, anything that can vary. Now, the astute among you have heard me say temperature now for both. And you're going, how can we do a temperature sensor with both, or a pressure sensor with both, digital or analog? Well, A, you can get just a digital, discrete temperature sensor, all right? If you think about how your air compressor at your house works, if anyone has like an air compressor, right? You plug that thing in, it compresses up to 150 psi, then it stops, or 130 psi, and then like 120, 110, 100, somewhere around there, it turns back on. That is a simple pressure switch that once there's enough pressure, it pops up, and then as the pressure decreases, the spring, it doesn't need as much power, much pressure to stay open. So once it stays open, and then once the pressure drops too much, it closes, and it turns the thing back on. So it is a discrete on-off sensor. It's a really kind of ingenious one, because it's like, oh yeah, this one accepts the range, so that way your compressor doesn't drop 1 psi and instantly turn back on. All right, so it's really quite an interesting sensor to have. But an analog one could do the same thing, but that would allow you to actually program those points. So you could be like, not just turn the compressor on when the pressure is too low and off when it's too high. No, you could be like, if the pressure is at 130 psi, stop, and I need to turn back on 125. Like only a 5 psi window I want to be not having compressed air, the compressor running for. Because whatever output device you have, either A, uses so much volume that once you have a little drop in pressure, you need to kick it on right away to keep pressure high enough because it's just dumping so much air, or B, your thing is just so sensitive to air pressure that you can't have those fluctuations. You need to keep it consistent. So there are times when that could be your need. But anyway, analog it's a great option in the long run. And the last thing on this slide is the analog comparator. Right? That is a little device, and I've tried to find these, and I've failed miserably. So I don't know if I'm using the wrong terminology. I got this right off of our little assembly system over there, because there's one on there for the height sensor. We're actually detecting the height of the discs. It's a little analog comparator, and what it is it's a device like this, and you've got 2 knobs on it. And you run your analog sensor into it at the top, and you've got 3 discrete outputs on the bottom. And what you have here is, this is your low level, this is your high level. So that analog signal comes in, and you have a part there, and you say anything that's less than this magical dial position is too short. Anything greater than this, greater than this one is too tall. So anything between those is an acceptable height. And then on the bottom, we have a low, acceptable, and a high signal. So all you have to do to tune that is you just twist the little dials and you're good to go. Now the benefit here is you can use just one wire, or you can use all 3 of those wires. You don't have to wire everything up to your PLC. You could say, I don't care if it's low or high, all I care about is it an acceptable height, and you could program that. Again, for a pressure system with this, you could say, whenever this low signal becomes true, turn the compressor on. Whenever the high one becomes true, turn the compressor off. We don't care about acceptable. Like, just ignore the acceptable. So you have options there, but it's a nice little simple device that will take an analog input and convert it to a digital output, which is really nice, or a discrete output. I hate the word digital. I don't know if I've told you that. Everything, I'm like, it's a digital. It's, it's a 0 or a 1. To me, that's what digital means. But people think about digital and they're thinking about like pulsing communications and things like that. It's like, yeah, not truly digital. I mean, yes, that is digital, but not digital that I'm talking about. But anyway, the analog comparator, it's just really nice because you can just tweak those dials ever so slightly as, as the system's not running. But, load a part in and say, this one's just barely too short. You just turn the dial until it turns on. Then you put one that's just barely too high in and you turn the dial till it's there, and it's like, okay, now we're good. And that's how you tune the system. Yeah, someone at some point must have tweaked those dials on me somewhere along the line, because one day I just rejecting everything. Gotta go figure out why. But I got it. But anyway, so that's what an analog comparator is. So I really need to find out what the better terminology for these is, because the only ones I can find are on eBay. I'm like, these have got to exist somewhere. Should just make one. That's really what it comes down to. Also, going back to current measurements, this is normally, I believe, a voltage measurement that we're using a very precise resistor for. So we're actually measuring the voltage because we know the resistor value, and by measuring the voltage, we can figure out the current. So it's still just a voltage measurement, but we're just saying, okay, we know the current is going to be, this based off the resistor, so we can measure the voltage. All right. That is actually how a multimeter works. One of these. Where's my mouse? Here we go. One of these bad boys. That's all it's doing inside. It's got a current capability, and there is a shunt, which is basically a piece of metal or resistor with a very low resistance, but a very accurate resistance that they know, and they measure the voltage drop across that resistor to determine the current draw. So same idea is going on inside the PLCs. So anyway, all right. So here we've got a bit of an example here. So in the world of analog, you'd have this beautiful curved straight line going through there, right? But when we convert it to digital, it becomes stepped. All right. The world of analog and digital don't truly interact well. All right. If you ever think about like film photography, like that doesn't have pixels on it. Everything is analog. It's like this perfect transition from one piece to the next. So you don't have to worry about like, if I zoom in on this, what's going to happen? In theory, analog, I think you can basically like zoom in on much as you want. Like you can enlarge it kind of as much as you want without losing too much quality, because it's how the system works. The world of digital, we can't do that. Obviously, when you enlarge things, you start seeing the pixels. In fact, when we're using the projector, if you actually look at it closely, you can see each square pixel. It's because of how it works. It's kind of funny to me. But that's a different story. But anyway, analog to digital converters, ADCs. All right. They are rated. I'm going to use the word rated. It's not probably the proper term here, but they are rated in how many bits they are. All right. So if you have a 0 to 10 volt range, we're just going to stick with that. This makes my life kind of easy. And you use an 8-bit A to C. All right. You have 256 steps in that range. So that means from 0 to 110 volts, you would have 256 different steps. So that would be 0.039 volts per step. All right. So that is the smallest deviation of change that you can accept, 0.039, which seems like a freaking lot between 0 and 10 volts, right? Now let's just make our lives here really simple. If your temperature sensor outputs a signal between 0 and 10 volts, because that's how it's rated, but it can measure between 0 degrees Fahrenheit and 256 degrees Fahrenheit, you have 1 degree of resolution. So you only can detect a 1 degree temperature change. All right? Now, I don't know. Yeah, anyway, let's just go here. Now, if we went up to, say, a 10-bit, which would be 1024, you would now be able to go down to about 1/4 of a degree of change. So you've just changed how many steps, right? So you went from having, as many steps in this picture. Let me go ahead and clear my ink. You went from having this many steps to now doing, here we go. You just double the triple or quadruple the number of steps by going from an 8-bit to a 10-bit. So that resolution is very important for you. And it's a game that you have to play. It's like, I need high resolution. I need to be able to tell a quarter of a degree or an eighth of a degree. Well, you have two options. Option one is find a better A to C. So instead of that 8-bit, you go to that 10-bit or 12-bit or whatever, however many bits it is that you need. That would be option one. Option two is you could find a temperature sensor with just smaller range. So if you only care, how often, if you're like, okay, we're trying to keep a room at 50 degrees, do you really need between 0 and 256? No. You need between probably 40 and 80 or something like that. So you could find a temperature sensor that is smaller, the range is smaller, so you would have less degrees over that entire range, which would increase your resolution. So analog, there's so many little funky games that you have to play. Now, luckily, many industrial applications, like keeping things to the 10th of a degree, probably isn't going to matter. It's like, you need to bring this this tank up to boiling. It's like, okay, we need to monitor that, but I don't care whether it's 100 degrees Celsius or 105 degrees Celsius. It just needs to boil. So, in that aspect, you're probably going to be okay for resolution, but just something to think about. The other thing I have up on here is PWM, so digital to analog conversion. So that's taking it the opposite way. Now, oftentimes when we are changing the value of something, we're actually pulsing it when it comes to the world of DC. So it's how fast are you turning that signal on and off, basically. This comes back to all right, I've got 10 volts and I've got 0 volts, right? So if I need a 10-volt signal, I would just send, 10 volts. It's really easy. If I need 5 volts, though, how do I do that? How do I send 10 volts out but only get 5 volts of actual? And what we would typically do is you would turn this on for half a cycle and then off, and then on, and then off, and then on, and then off. So it's 50% on, 50% off, and that would make it look like it's outputting 5 volts. Now you may be going, how? I can see the 10 volts and 0 volts, right? Well, it's just doing it at 10,000 hertz or something. So it's doing it super fast. So when the receiving device sees that, it's saying on and off, it can't measure that quickly. So it's actually averaging it. And that's how we would see only 5 volts or something. And if you really wanted to expand on that, you would put maybe some inductors and some capacitors in there to help resist the change, especially inductors. They don't like to change. Once current's flowing, they want to keep the current flowing. So by pulsing an inductor, it will help average out that for you. I wish I had an inductor and stuff up here so I could actually show you that and be like, here, look, this is without an inductor, and you see the pulses. This is with an inductor, and the pulses wouldn't be as noticeable. So I guess inductors resist the change of current flow. Capacitors are like a battery, so those would charge up some. So I would do an inductor and then a capacitor if you really needed to kind of help smooth things out some. But that's basically how we'd be doing this with a digital analog. There are some other ways to do it, but that's the one that I know the most. It's just pulsing it at super high frequencies, and then you're like, I need 2.5 volts. So it would be a 4-to-1 duty cycle, or 3-to-1. 25% on, 75% off. So it would just change how long that pulse is on for. By doing it super high frequency, most things don't tell the difference. So, questions on analog? Not as of right now. Okay, so this leads us to the world of HART. All right, HART is Highway Addressable Remote Transducer. And this is a smart instrumentation field bus. This is a protocol designed for applications where actual data is collected from instruments, sensors, and actuators by digital communication techniques. That's a mouthful, isn't it? Yeah. So this will allow you to do things like diagnostics on your sensors, memory for storing configuration or information, such as tag numbers, things like that. Yeah, do adjustments. So maybe adjust, like, calibrate your sensor. It's like, oh, it's 32 degrees in here. You look at another sensor, you're like, no, it's only 24 degrees in here. Let's tweak that down. All right. And it's a 4 to 20 milliamp digital hybrid communication. Hence why we had to talk about analog first. So here we have the protocol. This was originally developed by Rosemount. All right. This is considered to be an open standard, and it's a hybrid. So it reuses the 4 to 20 milliamp instrumentation cabling. So this is truly designed to be updating those old analog sensors. So it's like, oh, we already have these analog sensors out there. We need, some better technology, or we just need to replace the sensor. HART is kind of like trying to put its foot in the door saying, you want to use us. You don't want to just put another one of those boring old sensors in. You want our fancy sensor. And, all other wonderful things. They're going, well, why? Well, anyway. So what we're doing is we are superimposing digital signals on the analog ones. All right. That is the name of the game here. And we will, so this does this with frequency shift keying. So that's what FSK is. And this is a technique based on the Bell 202 communication standard. Where have you guys heard the word Bell before in the world of industry? Old school telephones, right? Yeah. Yeah, exactly. So this was based on their communication standard. I think this is actually how you have caller ID on your home phone. All right. So if you still have a home phone, I know that's starting to be like a big woo home phone. But back when caller ID was first invented, they didn't add more wires to your telephone. Right, you still only had 2 wires going to your phone, which that alone dumbfounds me. I'm like, how do I make a phone call in and outbound on 2 wires and not have a battery or anything on the phone itself? That just blows my mind still, but that's a problem for another day. But the same thing was what they're doing here with caller ID. They're using the analog phone signal that you'd get to your phone, and they're superimposing this digital signal on it. So that way your phone could receive it and go, oh, the phone number that's calling you is, and show it on a little screen. It's also why your phone with caller ID either has a battery or is plugged in. Just a fun side note for you there. But anyway, so we're going to use FSK for this. And what we're doing is we have 2 individual frequencies, typically 1200 and 2200 hertz. All right. And that's what you can see going on here. So there is your 2200 hertz. There's your 1200. 2200. All right. So the 2200 represents a 1 and the 1200 represents a 0. All right. And because we are just superimposing this on there, we're not actually changing the current flow, because we have high and low current, by doing this, it still averages out to be the same signal being sent. All right. So, if I have my little chart here, right, and here's 20 milliamps, here's 0, and I'm sending this signal right here, all they're doing is they're now imposing this frequency on top of that. So the average current flow is still the exact same. And they're, again, relying on the fact that devices don't see these high frequencies. They have to average them to be able to then do this. So the frequency, the digital side is just measuring the frequency. So it's saying 2200 or 1200 back and forth respectively. And then the analog is just averaging it out, still seeing the same current flow that it would before. So we're not actually changing the 420 milliamp signal at all. I mean, technically, yes, it's changed, but based on the receiving PLC, it's not changed because there's nothing different there. This is also how, in the long run, how Ethernet over power works. If any of you guys have seen those devices you plug into an outlet and then you just plug an Ethernet cable into it, and then somewhere else in your house you plug one in, and then you plug an Ethernet cable, you get Ethernet over it. It's the same general idea. We're just introducing another sine wave on top of our sine wave, and it's able to separate those out. I'm always curious. I'm like, I wonder how far I could take that. Like, if I plug one in my house and my neighbor's house, technically they're still connected to the same power lines. Could it work? That might be going through a transformer, so that would be, up in frequency. So I'm like, I don't know how that would work, but I'm just kind of curious to know if it would work at all. I don't want to spend the money on one just to, try that one activity, but it'd be kind of interesting to me. I think those are also limited to 100 megasecond, not a gig. So Anyway, what? Yeah, it'd be fun to try. Or like from this building to the next building, just plug one in here and go, okay, how many rooms over can I go? So transmission modes. This is going to be a poll response mode. So the master polls each smart device. Yes, back to the whole master slave thing. All right. So typically, how this would be wired is you have your PLC here, PLC, and you've got your analog input card, and you've got your your 420 milliamp signals going out to your sensor, whatever it is. That's our temperature sensor. So this would be the slave device per se. So this would be the PLC is the master. So it goes, hey, I need this information, and that smart device goes, yes, sir, and sends back that information to you. All right. Overall, a very simple thing. This can also run in burst broadcast mode. And in this mode, the field device just continually transmits the process data without the need for hosts on the request. So it's just like, hey, here's some information. And then the PLC is like, yeah, I don't care. It's like, hey, here's some information. I don't care. Hey, here's some. Yeah, you're right. I care now. It's been too long. Give me that updated information. So it's actually checking it in that aspect. So this could run in a master slave, or it could run in a burst or broadcast mode. I think one of the things that this depends on is, the master slave, the poll response option. I believe you can have multiple HART devices on one network. Now, obviously, the whole sending a single analog signal at the same time might screw things up. So that you would have to have special HART devices enabled the right way. But the burst broadcast mode can't do that because obviously if two broadcasts at the same time, PLC is getting mixed information. So partially depends on how many devices you're trying to run off that single analog cable that's already ran. So something to think about. So in the burst broadcast mode, it can be fairly fast, up to 3.7 times per second. So, that's pretty quick in the long run. So, each their own. And this protocol is implemented on OSI model using layers 1, 2, and 7. All right, so just again, so you guys can see the whole OSI model, 1, 2, and 7. You can see how that spam model just keeps coming back, doesn't it? Yeah, I still hate that thing, like remembering it. It's like, well, which layer does this operate? Network people, really good network people, just really know it. It's just like, oh, I need to defend against attacks at level 3. And how are we going to do that? It's like, what's level 3 again? So, something to think about. So, we have 3 mode options. You can do it in conjunction with the 420 milliamp mode. You can do it in conjunction with other field devices in a multi-drop mode, or you can do it in point-to-mode mode with only one field device broadcasting in burst mode. All right. So mode 1, that would be your traditional, you have your HART analog sensor out there. The main data, the pressure, or what we'll just go with pressure in this instance, is still being transmitted over 420 milliamps. So it's still sending out that analog signal, and then the other information, the HART protocol, that PLC is then requesting it, saying, hey, I need this. It's going, yep, here you go. All right, so you still have that 420 milliamp for its main signal, like the really, truly, as far as I'm concerned, super important aspect. But you still have that HART for the rest of the stuff, maybe battery level, or what mode is it in, or whatever other information is going on. Maybe a diagnostic mode to make sure it's actually working correctly, type of thing. So that'd be mode 1. Mode 2, this is going to say a multi-drop. All right. So this would be getting rid of the 420 milliamp. You're still using the wires, but now it's just HART over that. So again, this would be like a master-slave setup with just using the old 420 milliamp wires. And then 3 is that device just broadcasting in burst mode, saying, hey, here's my information. And again, it's one device per HART port, basically. Yeah, okay. So on that last one, the analog output is set to a constant 4 milliamp and only communicates digitally. So, yeah. So this one again would be, whatever the analog signal value is, and then we're pulsing on top of it. This one would be probably, I guess, no. Yep. You would have no analog voltage, and then you would just be communicating. Basically, that's your master slave setup. And the third one again is you have just a constant 4 milliamps, and then you're just broadcasting information on top of that. So ever so slightly different. And with the second one, If you set the polling address to a number greater than 0, the HART device just assumes that it's now a multi-drop environment. So it again, kind of doesn't expect the analog information. So going on here, we have a physical layer. So this is 1200 baud. That's our communication speed. So that is good. We are... yeah, okay. We have two different methods of communications. We have the analog, again, 420 milliamp, and then we have our digital FSK, the frequency shift keying. All right. So there's that. You can have a device that looks like what I have here on the right side of the screen. That is your HART handheld communicator. This could be a secondary master device. So you could still have your PLC hooked up, and then you could just be like, hook this up with some like alligator clips to the wires or sensor or something. And then this could do some polling as well. So you could go, hey, give me this information, and the device would then respond to you. So this is a really nice device to be able to just like pop in there and read sensor values. So you know, it's like anywhere you can connect this thing to the wire, you could then get information off that HART network. So in that aspect, it's really freaking nice. This can read that information, it can write information, it can have a range, it can use for calibration. Yeah, it's great. And as I said, this can be connected anywhere in the bus as long as the loop impedance is at least 230 ohms. So that is something that you need to think about, but it's really not the biggest problem in the world. But yeah, I mean, that looks like a really weird device. I don't know about you guys, but it's obviously designed to fit in one hand. It's really kind of interesting to see technology nowadays. It's like, okay, cell phones. How has that replaced everything? And you look at something like this, and you're like, really? That was a device at some point? And probably still being used somewhere? But yeah, got the job done. It did what it was needed to do. And it might have even been touchscreen looking at it. Maybe not, but looks like it to me. All right, so some commands. We've got universal commands, all right? This includes things like, okay, let's just go through the three. We've got universal commands, common practice commands, and device-specific commands. And I think I'm going to talk about all of those separately. So here you have a list of universal commands. Nothing super fancy here, but manufacturer, device type, primary variable, and its units. That units one is really important, right? Is it volts? Is it temperature? Is it millivolts? Is it degrees Celsius or Fahrenheit? Again, what are we communicating with? And so that can be a very important thing for you to be able to pull up is that unit that's being used. The current output percent, defined mathematicals. I don't need to read all of these. You guys can just read them yourself. But so there's a lot of universal commands. That's like every HART device has these. Again, this is considered to be an open standard. So got to take that with a grain of salt, is in my opinion. Some practice commands. This is a lot smaller. I should edit this. 1 second. All right, so yeah, anyway. Common practice commands, set a fixed output current, self-test, master reset, write values, trim things. So again, really useful to be able to plug in that handheld device and be able to go through these things and say, all right, let's test this sensor. Is it working? And be able to hit a button and go, yep, all right, we got this value. That's what we're expecting. And the fixed output current, so that's to make sure that the value is actually going to change. So maybe you can say output 5 milliamps, send 5 milliamps out for you and go, yep, we're working. Okay, so that hasn't died. So great for testing things. And then some other instrument-specific commands. I'm going to click back into this. Start, stop, totalizers, density calibrations, mass flow. Yeah, it's all sorts of little things, but it's still just really quite handy to be able to have all of those different options is what it comes down to. So the HART protocol. A lot of benefits here. So we have both analog and digital over the same wire. That is assuming one device. So that is something important to kind of keep in the back of your mind. I guess you could technically, and I'd be really intrigued how to do this, but you could probably hack it and put like a HART device that is set up for digital only and an analog device, analog only, and still have both of that information coming at the same time. It'd be a really funky configuration because the PLC would probably see it all as one device, and you're like, well, it's actually two, right? The analog value is its own device, and the digital stuff is all its own device. So that'd be really kind of a funky thing to be trying to do, but you could probably technically get away with it if you set all the configurations just like perfectly. Probably not worth it in the industrial environment, but for me who's like, I wonder if I can do this, it's the type of thing I would try and do. This does allow us as other devices to use the analog highway, basically, so that's kind of nice. Multiple masters, that's a big one. Oftentimes these things, it's a single master device, and that's all you're allowed to have. And once you start getting multiple masters, that's when the fights start beginning, because it's like, well, do I listen to this one or do I listen to that one? And who's communicating? And when are they communicating? So the fact that this does allow multiple master devices is really quite a good thing. It's multiple smart devices, same highway. That's like every freaking smart network we've talked about so far. I guess Ethernet, not technically. That is, everyone has its own wire. I mean, yes, we're all sharing things once we get to switches and stuff, but everything still is like point to point. But like device net, that has been a drop, where you just like tap into the wires and you just put another device on it, type of thing. So that one's not too crazy. We do have that long distance communications over telephone lines. Again, this is where they kind of said, okay, this is what we're going to do. They took that from the analog, the telephone world. Think about how far your telephone wires used to go before they terminated somewhere. I know. Talking about telephones nowadays is just weird. I don't have any of you guys have an actual landline in your house? Yeah. That's how most landlines are nowadays. It's like, hey, Comcast, I want a telephone. They're like, okay. And they give you a router with a telephone port on it. So you plug your telephone into it, and it's technically a phone. It's a landline, right? Your address at your house, but it goes into the IP network and then over that way. So, or it's actually 100% IP, where it's just like an IP phone, Ethernet cord on it, and it just connects to its own service. It doesn't go through Comcast at all. So, a lot of weird options there. Yeah, so long distance, that's good. Alternative transmission modes, right? We've got the analog digital, we've got just the digital, and then we've got the multiple device digital option. So there's 3 different modes, that's good. We've got flexible structuring, up to 256 process variables in any smart field device, so that's a lot going on there. So HART is, in the long run, it's a great little technology, right? Every analog input card is not HART capable. That is definitely something that you need to keep in mind. So just don't be like, oh, we've got analog, we can put this HART sensor on there. Well, you probably can, but it's going to be as dumb as an analog sensor. All right. So you're going to have to configure it, only output the analog signal, or analog with the digital over it, and you're just never going to get the digital because all you have is an analog input card. So you can have an analog input with HART capabilities. So that's just, again, something to kind of keep in the back brain there. I wonder if my analog cards, probably not, too cheap. So there's HART. It's great in the long run. It's reusing wires that are already there. Think about the time savings that would have you in industry. It's like, oh, we need more information from that one sensor. Okay, let's put a HART sensor there, put a HART input for the analog card, and we don't have to run any new wires. So yeah, it's going to cost you new devices, but it doesn't cost you any man hours to run the wires, which means that your upgrade time could be a matter of minutes, right? Because it's like, hey, you two, go over there, replace that sensor. You two, replace that input card. Third person's on the PLC saying, okay, here's going to be the new input card. Here's where things are going to be wired. Update the tags, and boom, you're done. Compared to, okay, we got to run a new wire for this, and depending on where you're running that wire, you may have to do machine down for that wire run. Oh, that's not going to make your boss happy. So there's a lot going on, a lot of benefits here for this HART technology. But there's obviously some downsides to it as well.